guys, BBI here. I want to stop and say thanks for tuning in and checking out whatever the video is about that's about ready to come up next. If you could take a minute and hit subscribe, I greatly appreciate it. And if you enjoy what you've seen here, make sure to hit the like button. We'd greatly appreciate your support. Anyhow, guys, all that aside, let's get on with the show. Look, it's SP220 time. Hallelujah. Okay, let's grab our little flat blade here. There's a lot going on inside this little box that we're going to have to go through and redo. Basically completely rewire this. There's some things here that scare me. It's okay. We can fix it. We have that technology here. Wow. Wow. Okay, so the primary issue that this gentleman has is he said that he turned it on. First he tried to do, this is the EPD, electronic product design, replacement transformer right here. Then over here is the EPD electronic product design replacement filament transformer. Both of these are good solid products. Then he went and he replaced the Harbach board, or replaced the high voltage board with the Harbach board. And then he replaced the capacitor bank with the Harbach board. But how it was done was not safe by any means. This has got high voltage on it. It was 600 volts worth of insulation. This has got high voltage on it with unknown amount of insulation on it. This has got high voltage on it, at least ground, this would be positive. This is our high voltage positive, and it's got 2 joints in it. Same thing going on here. All of this has to be rebuilt. And let me show you why. You're gonna love this. Pull the camera off the tripod here. It's a trace. Evaporated. This capacitor's not soldered in. This one's not soldered in. That one's not soldered in. I can see so much stuff going on just in this space alone that I have to address. And then we come around to the bottom side. What is this? I don't... Needless to say, I'm pretty sure I got my work cut out for me. Gentlemen, let us begin the nightmare. Oh, it's so much fun. Okay, on that catastrophic of a failure. On this catastrophic of a failure, we can only assume that we wiped out something here on our high voltage board. So I went ahead and I broke it down to the point where we've got our face off. Nothing on the input circuitry looks too chooched, so I was just talking with my friend Paul, 222. He had a problem with this resistor and then its coupled paired diode that goes with it. And gone to an open. There's a 220k resistor here, or a 2.2k, 2200 ohm resistor that's here that always burns up if it gets driven too hard. So I want to look at that. Taking a good look at our band switch, and it looks like everything's fairly intact there, but instead of trying to deal with having the face and moving the face around a bunch, I just went ahead and I disconnected all the leads that go to it. And we'll just carefully wind these up out of the way for the moment. There's a lot going on here. But I can only assume because this transformer is, I think, in backwards. But we'll figure that out in a minute. Let's go over here. Got ourselves set on diode check. Checking for a hard open. This is our bias circuit. It's okay. Now let's go look at our rectifier pack, which is literally laying on our filament transformer. It's not open. It's not open. So I can't get to that leg. I can. That's not open. That half the rectifier circuit is good. Not open. Not open. Not open. Wow. Wow. Okay, so the high voltage board is okay. We got to change how this is mounted. Just so I told the customer some of this stuff is wrong, some of this stuff is unsafe, and our primary goal is to make it so that everything is safe. And I said it's not that it's going to be that labor and well, it's going to be time intensive. Might take a little bit of labor, but it's going to be a little bit time intensive. The bottom side is what's got me concerned. It's a nightmare of missed connections, I guess would be the best way to put it.
Yes, master. Right.
It's my teacher. Shit. Come here. This does not look right to me. Some of these wires and the gauges that are hooked up to things, this doesn't. I've never done one of these filaments before, so I've got to physically remove this transformer here so I can verify how it's hooked up. Now once I get that verified, then I can figure out what I got to do for placement, because it cannot be up against that rectifier board. The low voltage turn of the filament, the secondary on this transformer, is right up against the 1600 volts of the voltage doubler circuit on the high voltage board. And what we have here is where this leg of the diode is starting to rub through the insulation on the transformer. Okay. Alright. So I went ahead and I unwired the primary side, and we're going to move all of our wiring to this hole. We're going to abandon this hole. We're going to slide the transformer forward just a hair, and that'll give me the opportunity to redo all this stuff here, so there's not all these butt splices. And then I'm going to do the same thing with the high voltage board and all the high voltage circuits. I'm going to make that so that they're uncut, continuous, properly insulated pieces of wire for safety reasons. And then we got to come down here, because I'm on the filament side of the thing. I'm going to come down here, I'm going to completely rewire this whole section and start over. But it starts with me drilling this new hole in the base of the, right here, drilling this new hole. Then I got to drill another one here, which is going to be here, so we can move the transformer forward. And we got to be careful how far we move it forward. Let me show you why. Because in the stock hole, we're on the rectifier board, so we come forward just a hair, so we can get a little bit of clearance on the rectifier board. But that puts us right up against our mode switches. These guys. So we got to watch our clearances there. So I'm going to mock mount this thing, and then I got to remount the face and make sure that we got clearance. All right. There's a screw rolling around in this meter. I don't know why. There is. Perfect. Hold tight, but perfect. I got clearance here. I got clearance on my variable. There's no torque pressure on nothing. Cool. Now to take it all apart and rewire the high voltage board. And I'm glad I've wired a couple of these over the years. So we just removed all of this hibby-jibby here. And we've completely rewired the high voltage board, which thoroughly tests. I can't believe it. With this, all this burned up schmoo here up top, up here on the rectifier, on the capacitor bank. God, I gotta quit touching it. I went ahead and replaced it with 15,000 volt wire, or 10,000 volt wire everywhere, and got rid of this. This is dangerous. This is like 600 volt wire. This was the high voltage lead. It's all broken and stuff. That's not what caused our problem, but I have to fix this for me to feel safe about it being with my name on it, if that makes any sense. So now what we've got to do is we've got to address the elephant in the room. This thing here, this whole mess here, and this stuff here, this isn't right. This isn't safe, nor is this right. And how we overcome that is that we're going to have to rotate the transformer. The way this is designed to sits the other way around. So then I got to go through, and there's a couple of these that I've got to redo. Like this blue lead, I got to make it all so everything's got the same length of extension to it, and then we'll probably put it in some nylon spiral wrap or something, clean this up. Even though this is in theory correct. And then why I'm up here after I get that finished, so we can bring these leads, the actual leads, as long as they need to be, get them into the appropriate place. Okay, so we got to rotate this fully around, like fully around. So once we get that correct, then we can go and address how the filament transformer was wired in, and we can work on the bottom. And then we're going to ground the grids and all that other kind of cutesy stuff. But before I get that far along, I'm going to flip the transformer, and then I got to take this capacitance bank out and measure what's going on with our electrolytics here. So, okay, All brand new Teflon. Stranded Teflon, by the way. Not solid single strand, solid core. If you torque on it too many times, it breaks. An all new high voltage lead. Moving on. I always forget how big of a pain in the knob it is to mount one of these things. Anyhow, all plugged in, nice and neat and clean. We made it with about 1/16 of an inch of wire to spare. Make it over to our high voltage board on the connection there, and our little silicone boot wire will go right here, all nice and clean and neat. Now let's un-F this. So let's pull the whole capacitor bank out. Let's see what we find here. So repaired the trace, cleaned all the carbon score off. Now, what I'm going to do is not going to make a whole lot of sense to a lot of you guys, but I turned on our cap tester. But BBI, you're checking it in line. It doesn't matter. Doesn't matter. 293 puff. I'll back that up here in a second with some proof. 288 puff. $290 puff. But BBI, there's resistors across there. My God, you're crazy. No, I'm not. 290. 292.5. 292.0. That's UF. Sorry, not PF. That's this one here. 291 UF. And now the one that took the brunt of the load, $293. Doesn't matter. At least not in this particular situation. And that's because the resistance is so high at 100K a piece on the resistors on this bleeder circuit. So you're going to ask yourself, well, how'd you repair the trace? Well, they make this really cool stuff called copper tape. Anybody that's close to me, I've turned them on to this tech. It's something I've been cruising along with over here for a couple of years now. I actually got it from a Adam Savage Builds YouTube video. This is fully solderable. This is pure copper with a mild adhesive on it. I cut it out in the exact same size space of the old trace that has disappeared and gone up in smoke. So what we just demonstrated to ourselves that all of these caps are supposedly 330s, but they're all low. Not so low that I'd be concerned, but they're still low. I don't like using these caps. These little short bastards. I know they're computer grade, but why did we arc? And why did we arc here? This is the middle of the bridge. It's positive, negative, positive, negative, positive, negative, negative, positive, negative, positive, negative, positive, positive. The only thing I can think is because these other joints up here on the bridge weren't fully soldered here and here. I mean, clearly not soldered in place. It's the only thing I can think. So the AC that's present here backfed through this end of the leg of the bridge, but it should have wiped out these caps, but the caps are good. I'm going to clean this up a little bit more. I'm going to solder these parts back in and we're going to install it. We're going to go on now and start taking this apart and getting this so it's a little bit more organized. It makes a little bit better sense. These things are cute. Absolutely not necessary, but they're cute. We're going to clean all this up And then we're going to ground the grids, and then we're going to start doing voltage testing on it. We'll put this back together for now. Let's test one last thing. So now what we're going to test is our conductivity through all the caps in the chain for a total sum value of, should be about 73, 72 UF. Look at that. We should see this on the other side too. I'll live with that. Balanced. What that tells us is that we got conductivity through the entire circuit. Both sides. So we're going to have ground, which is going to finish, you got your rectifier diamond. This is a string of diodes, this is a string of diodes. And then instead of having a string of diodes here and a string of diodes here, you're going to feed AC here and AC here into the diamond. Out one side, you're going to get positive. Usually this side, top side, positive, and then the bottom side you're going to get negative, right? Well, we replaced half that string of diodes, so we feed AC in on this string of diodes, and on this side of the diodes you're going to feed AC in, but there's no diode. Now we're using a capacitor bank, so voltage doubler works. So we got conductivity through this leg of capacitors, and we've got conductivity through this leg of capacitors, down through this set of 4 and up through that set of 4, and this is our center tab, thus completing the diamond. This will work. Well, this is where we're at. Top side's completed. Now I gotta go unbork the bottom side. Just changed a small few things here. It's okay. It's okay. To my guy that tried to do this, it was a good valiant attempt. You got to remember, I do this every day, all day long. This is what I do. And this should have worked. I mean, if you would have had a little bit more solder over here on some of these other legs, I think you probably would have been all right. But remember, this is what I do. So all of this back here has been cleaned up. We reorientated the transformer. Caps are all redone. High voltage board. The only thing I didn't test was all the peripheral stuff, like our glitch resistor to ground, that kind of thing. It doesn't show any visible damage, but and then I crawled over the high voltage board like crazy, and I don't see anything on there that makes me concerned. We did replace all the high voltage lead. We've got good physical separation and replaced all the wire. So let's go ahead and let's flip it over. And now all we got to simply do is formulate a game plan for this. So take a quick picture of this so we can have a before and an after. All right. So here we are once again. We're going to clean this whole mess up over here. We're going to reattach our filament transformer. Not that it was not... okay. There was a couple things that were not correct. Period. But they wouldn't have caused the problem that we've seen. It would have caused the keying relay to burn up and this capacitor to explode. So we're going to go ahead and we're going to check our cap. And then we're going to rebuild this whole end of the circuit over here, which is our 110 volt DC switch circuit for the relay. And we're going to organize this. Then we're going to come over here and we're going to ground our grids, and we're going to work a little bit on the tubes. But the first things first is we went ahead and we disconnected, labeled, and disconnected what our filament leads were. And then I got a bunch of splices and stuff that I need to remove in here and reroute wires so they look nice and pretty. And we got to go add a diode. For some reason there's a diode that goes from ground to this post here. For some reason there's a diode that has been added down here. And no. It'll cause a backfeed across the circuit. And for this to work, we have to give the transformer ground, which we have, through this spliced wire, have to give this lead ground, and then we have to, well, I'll show you. That's where we're at. I'm going to start back here in the back corner of the box though, and I'm going to take this jumper system out. I'm going to go ahead and resolder it back onto the breakout pins on the breakers. And there's what comes up to the front. Now somebody did do a very beautiful heat shrink job up here on the front switch, which we're going to try and keep. But a lot of this is just the way it was wired wasn't, I don't want to use the word bad, but I'll say that it wasn't absolutely spot on correct. So yeah, we'll get her done. Okay, so we had a couple little things on the bottom side that weren't quite appropriate. Now I've gone and I've converted this back to 110 so I can use it on the Variac and slowly bring it online. That'll allow us to test everything as we turn it on slowly. Because if we hit this thing, just plug it in and there's a problem, we can have arc and spark and cause a whole bunch more problems. So went through the bottom side of this thing, cleaned it all up, took a bunch of splices and stuff out of it, and hand tied this with wax line, so it's all nice and hand tied. Now, since I don't have a metering face on the front of this thing, I have no voltage reference. It's okay. Over here, we've got our 1000 to 1 reduction probe. So for every volt here represents 1000 volts. Everything past that decimal point right there. This is our low voltage side, which we have hooked up to our filament leads over here. And this is what's going to give our low voltage reference. Now over here we're controlling the whole thing with a Variac. Down here we have our 110 volt line, but we're going through these little 22 gauge jumpers. And the reason we're doing that, once again, is kind of like a shock absorber. So if there's a short or anything that takes place here and it's a catastrophic hard failure, it will get sucked up by these little tiny jumpers, and well, it's kind of like a secondary fuse, because we know that little 22 gauge jumper isn't going to carry a whole lot of current to this box. Okay, we don't have any tubes in it right now, so what we're looking for over here is for this to read 2900 some volts and for this to read roughly 5 volts. Okay, filament, high voltage. Ready? Here we go. Fan starting to turn. See the fan turning right back here. We've got 1600 volts on our doubler, 2000 volts on our doubler. Absolutely no resistance on the Variac. We're now at 110 volts. We've got 2,758 volts on our high voltage circuit. And 5.1 volts over here on our filament. Now we brought it up to 110, 2,945 volts. Remember, we've got a hard window at 3,000 volts on our capacitor bank. Now our capacitor bank is where all our problems started from. Remember, we got burned up traces, we've got melted down stuff, we had stuff not wired right. So we've got a very smooth turning on and turning off. Let's go over here. We're going to put this on the low voltage tap. Now we're going to watch this burn down. We should stop at about 22, 2190, somewhere in there. It's off by 40 something volts. That's perfect. 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 Back to the high volt setting. Perfect. Okay, now the next step is we're going to put tubes in it, and we're going to try and run it without the face on it. I put the face on last because there's so much torquing back and forth with the wires and stuff. I don't want to have a chance of anything breaking off. I don't really need the face on here to run the box for testing. I'm going to go and fiddly fart around with it, probably in the 10 meter position, and then we're going to make sure it's working in all modes, 80 through 10. So let me set up for that, and I think I'm going to convert this back over to 220, which is actually single phase 110, believe it or not. So I'll take these two jumpers out. I'm going to switch that over to a single jumper down the middle, which will make it single phase 110, or pardon me, single phase 220, or otherwise 110 volts. We'll get rid of all this stuff. We'll flip it over and let's get ready to run this thing. I want to try and make sure the band switch is good, our input signal's good, and make sure that we can get power out of this thing, and we're going to run it through the gambit. Then we'll put the face on it, then we'll put a sticker on it, and then it's going to go home. I'll be back. This thing runs like a raped animal. Check this out, guys. So we've got our RF junk anode caps on top here. We're using our ICOM 7300. We're on sideband. This is in 2,000 watt slug, 2,000 or 1,000 watt in average. About 50 bird, 100 peak. Check this out. 1,500 watts on 80 meters. Input tune. Non-existent. All right, moving on. All right, so yeah, look at all the knob position switches and settings. We'll get that taken care of in a minute, you guys. Here we are on 40 meters. Everything is before 1,000 watt slug and 2X, and so on and so on and so on. Same amount of drive. Let me step on my pedal. Flawless operation, I must say. Flawless. Alright, so the next stop on a world tour of the SB220 is 40 meters. 40 meters. Alright, drive power. Step on the pedal now, 2X position, 1,000 watt slug. Beautiful. Beautiful, oh, it's magic. Do you believe in magic? So where am I at now? 15 meters, I do believe. Yep, 15 meters. Okay. Same drive as before. Same output. Check it out. Alright. Last stop, 10 meters. Choo choo. Okay, 10 meters. 10 meters. Drive. A little bit lower than the rest of the bands for some reason on the ICOM 7300. Don't know why. I'm not going to ask some questions right at this minute. 1,200 instead of our 1,400. But the input tune is good. 1. Half a watt of input reflect. 1. 2. 1, 2, 1, 2. Okay, now we're done with you, ICOM. Thank you. Now, let's put the face on it. Let's reattach all of our meter leads and make sure everything's working with that. And then we're going to drive the holy bejesus out of it. Shall return. Well, that took a little bit of time to work out. So turn it on and start running the meters. And the voltmeter would sit just below 3,000 volts. As soon as I step on the pedal, it dropped down to 1,800. Okay, and the plate amp meter was going in reverse. So I automatically thought my plate amp meter wires are backwards. No. I slowed down, and I took a quick observation that that's a 1 ohm glitch resistor, by the way. That one right there. And there's a ton of space between my finger and the amp, by the way. It's a 1 ohm glitch resistor, and that's a 1,000 ohm resistor, and the 1,000 ohm resistor is where the 1 ohmer was at, and the 1 ohmer was where that was at. And then the center tap of the transformer was on the wrong connection, so I moved that wire over here, and then I brought my ground leg and I attached it, and it's that wire there. Sorry, not a big fan of sticking my fingers on 3000 volts. Anyhow, I had a couple wires on the board that were not right, had a couple parts in the wrong place on the board. Anyhow, I got all that flip-flopped and laid around correctly, and this is where we ended up. So, way off here in the background, we're going to have our watt meter. I'm going to run this thing. I'm going to show you here what we got. I'm going to run it the way it sits, just to show you the meters down there in the bottom right hand corner. So we got our zero signal back. The plate amp meter was not working whatsoever. It was running in reverse. Now it's moving forward. We got the appropriate amperage verified, by the way, with our flute clamp over ampering. And now we're going to hit it with, and we're going to translate over here to the watt meter. It's in 5x position, by the way. And I don't know how clearly that's going to come out camera. We'll zoom in on this in a minute. I'm going to hit it with about 250 watts of drive. It's 2800. It's exactly what I expect to see out of each one of these things when they leave here. It's 2800 to 2900 if I really hoop in the microphone. Let's look over here at the plate amp meter. That's reading accurately. Look at our voltage sag now. Remember, I was going to like 1000 volts. I have to say that the Gen 2 transformer from EPD is as solid as a brick shithouse. I'm impressed. The voltage sag on this is less than 400 volts. So we're working with an unregulated supply. We're sitting at about 3,300 volts. I step on a pedal, it's dropping to 3,000. And with nearly a full amp worth of load on it, we're dropping to 2,800, which is pretty stiff. It's hard to even get that stiff of a supply with a full bridge rectifier. See, voltage doublers do work, and I don't care what anybody says. We'll have this argument until they turn blue, and I'll just sit there and smile. Comes from the guy that's repaired 300 or 400 of these. I will tell you that a voltage doubler circuit does work as long as your transformer can keep up with the affected load. So instead of having like a 2 amp transformer, let's say at 2200 volts pre-rectified, we can get away with having like a 1200 or 1300 volt transformer, but instead of it being 2 amps, it's going to be 4. Okay, to get the same performance. Voltage doubler circuits work as long as the transformer can keep up with it. This EPD transformer that's in here, this guy is actually smaller than the stock transformer, and it produces more current. Better engineering, better core, better wire. Just saying. 900 bird. Okay, now that we're done fixating on the meters and we're showing that they're working and they're a valid unit of measure for this guy, let's go ahead and zoom in on here so you guys can get in on the digis. One. No, we're not on sideband, we're on AM. Run the dead key up here a little bit. 1. Run it just like an 80 meter AM guy. Okay, so last things first here. Let's look at the face of this amp. It's got a bunch of scribble majob on the front of it. I would normally completely clean the face of the amplifier and make it as clean and as pristine as possible. This guy's got a cheat sheet. Now, he's a smart guy. I know this because, well, he tried to attempt a lot of these modifications himself, and they weren't all technically correct, but I know he's smart enough to understand that we're going to use a flat blade screwdriver and you're going to go reload your box for whatever your system is at your house, I know that this is technically correct, where this knob is at, but we're out of phase with your index markings here. It's a flat blade screwdriver on this. It does not have the hex keys. So you'll be able to reorientate this to how you need it to run for your station. Alright, I'm going to leave that alone. This switch, I did have to replace it. The other one that was in here, this is what I was telling you on the phone, is this thing just spins, and as soon as these get a bend to them, they're kind of hard to index in the appropriate direction. See what I mean? This one does not spin. Straight up and down, it's not bent, but I did use your little rubber booty that was on the front of it. So, long and the short is, this thing was an animal. Here to tell you. Now I did put the horseshoe parasitics in here. And every once in a while I just have one that comes along where the horseshoe parasitics don't quite agree with it. This particular guy wanted to oscillate with the horseshoe parasitics in it. I'm going to send this with the amplifier. If you want to put these in there and try and make it work, you can spend time doing that. But what it's going to come down to is their orientation inside the deck. I'm not going to spend any more time on it. I put the stock parasitics back in it, which are perfectly minty fresh. Never been burned magically. Now, all that being said, Mr. Fisk, my friend, listen. These particular parts that I removed from the base of your amplifier, off the bottom of the sockets, because these are burned, tells me that you have a problem with one of your 3500Z tubes. I have about 15 3500Zs that are sitting here. If you need a new set of tubes, I've got brand new in the box IMAX, Amperex, and RF parts designs. Your grids are grounded. So if you had a catastrophic failure on one side, in the inside of your tube, you're going to know it as soon as you turn the amp on. It will pop your breaker. Everything else in your amplifier will be fine. So keep that in mind. Now, if you can remember what tube came out of what socket, it was this socket. I dare not get any closer than that. It was this socket right here. It was the tube that had the problem with it. Okay? I'm telling you, that's what caused this right here. Food for thought. Guys, I gotta put the armor back on this thing and I've got to be done. I'm gonna pull my tubes out of it after I let the tubes cool off. And I'm gonna get this thing crated and ready to go home in a wood box. We've had several instances now where these things are just getting bent up. The brown shitbox kickers give 0 Fs, if you know what I'm saying. So, look. The other thing I got to talk to you guys about is that I'm pretty much here to answer questions, at least for the next couple months. I've said this over and over and over and over and over and over and over in every single video. I'm not taking on any more new work. I'm just not. I have no physical room left to store all this stuff. I've got probably 25 SB220s in the shop right now that need to be repaired. I have approximately 300 to 700 other boxes that are here right now. I've banged and banged and banged on the door for the last month and a half since I've come home from the break, or almost 2 months now, and I've managed to repair about 75 amps. At that rate, I've got about a year's worth of work, year and a half worth of work on the shelf right now. I don't have any more room, you guys. So, I'm sorry. Unfortunately, for right now, at this time, I'm not able to take on any more work. Please bear with me. I'm doing the best that I can. And honestly, I'm this busy because you guys believe in me and you believe what I'm doing. And I say thanks. I just keep moving forward, one amplifier at a time. So on that note, I hope you guys enjoyed this video. Give me a thumbs up if you liked it. If not, call me on the phone and tell me to go sniff unicorn farts. I'll see you guys. I gotta run away. I got other stuff I gotta do. And believe it or not, I'm taking this show on the road. The next couple videos that come out from over here, you guys are going to absolutely freaking love, because I can't tell you where I'm going. I can't tell you what I'm doing. I'm here to tell you this is One part of this trip has been in planned works now for over 2 years, and I'm excited. And it is all 100% radio related, and I'm doing videos everywhere I go. So get ready, boys and girls. I'm out of here, and we're going mobile.